Hey guys, this is Mr. Bennett, and this is Unit 14, video number 3. We're going to talk about our last gas law, and it's called Dalton's Law of Partial Pressures. So in order to understand Dalton's Law, we need to return to the example of a gas bouncing around in a container. So if I draw that out here, we've got a gas, and we're just going to draw it as dots. We know that this gas, based on its kinetic energy, is bouncing around in the container. And every time it collides with the container, it creates a certain amount of force, or in basically our terms of class, it creates pressure, right? Collisions create pressure. So this gas is colliding, it's creating pressure within the container. Now let's imagine there's another container, same size and all that, but it contains a different gas. So I'm going to just represent that different gas by drawing little triangles, okay? And so the triangle is just saying it's a different substance, okay? If we want to give it an example, like a name, let's say this is CO2, and let's say that our original gas over here is hydrogen gas. Okay, so our little CO2 triangles are also bouncing around based off of their kinetic energy, and they're creating pressure as they collide with the container as well. Okay, and so there's certain factors that can come into play here. Okay, first of all, if we talk about hydrogen, hydrogen has a mass of 1 on the periodic table. It travels around as a diatomic, which means that we take that mass of 1 and we multiplied by 2. So hydrogen has a molar mass of 2 grams per mole. Okay, so in other words, a mole of hydrogen gas has a mass of 2 grams. Carbon dioxide, on the other hand, carbon has a mass of 12. Each oxygen has a mass of 16, and there's 2 of them. So what that means is the molar mass of carbon dioxide is 44 grams per mole. In other words, if you have a mole of carbon dioxide gas, it has a mass of 44. Now, the reason why these numbers are important is that what it says is that different gases, right, have different masses, different types of gas have different mass, and that's going to come into play when we talk about the pressure that they create when they collide with the container. Okay, if we say that they both have the same temperature, in other words, temperatures remaining constant, that means that the kinetic energy of this box is equal to, or at least the average kinetic energy, is equal to the average kinetic energy of this box as well. However, the mass of the two gases would be the equivalent of, say, a bicycle crashing into a gate or a wall, and a truck crashing into a gate or a wall. Okay, the mass over here is much, much less than the mass over here. Okay, so in other words, carbon dioxide with the same kinetic energy as hydrogen gas collides with the wall with greater force, creating therefore more pressure. Okay, so in other words, same kinetic energy, this gas creates a certain amount of pressure, and then this gas creates a different amount of pressure, right? We'll call it pressure 1 and pressure 2. Okay, so let's say that we want to take this gas and this gas, we're going to force them into the same container, same size, and we're going to keep the temperature the same as well. Okay, so let's draw our hydrogen gas. We had 5 of them over here, so I have 5 dots here, I have 5 dots here, and then let's add in our carbon dioxide gas, which was triangles. We had 4 of them, so I'm going to add 4 triangles. There we go. Let's put little action lines in here so we can see the collisions colliding with the container, right? So they're still moving around. They still have the same amount of average kinetic energy because we kept the temperature the same, right? That sort of thing. However, now we have more gas particles, right? And so the carbon dioxide, the little triangles, they're still colliding with the wall, creating pressure 2. And then the hydrogen type of gas particles, they're still colliding with the walls, creating pressure 1. So in other words, by putting them in the same container, we've taken the pressure that this gas creates, we've taken the pressure that this gas creates, and we've simply just added them together to create a total pressure. So if you have a mixture of gases within a container, the total pressure is really just a sum of the individual pressures that each gas in the mixture creates. So that gets us to Dalton's Law. Dalton's Law of Partial Pressure states that if volume and temperature are constant, so at constant volume and temperature, the total pressure of the container or whatever is equal to the sum, meaning we add up the sum of the partial pressures of the gases. The pressure that one gas creates is called the partial pressure. Okay, in other words, it's part of the total pressure. Okay, so if we mathematically were to draw that out, that means that the equation would be the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. dot 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 means that you keep adding in different pressures until you've added up all the gases that are in your mixture. So in our example up top with the boxes, we had 2 gases. So in other words, we had the pressure of gas 1 plus the pressure of gas 2. Okay, we wouldn't have a pressure of 3. If we had 5 gases, it would be pressure 1 plus pressure 2 plus pressure 3 plus pressure 4 plus pressure 5. Because we have 5 gases, they each provide pressure, we add them together and we get the total. Okay, so with Dalton's law, there are 2 types of problems that you can solve with this particular equation. The first type of problem is known as determining the total pressure. So in other words, you're trying to solve for this guy. Okay, so here's an example. Determine the total pressure of a gas mixture that contains oxygen, nitrogen, and helium. The partial pressures are, so in other words, the partial pressures are the pressures that each gas creates in that container. Okay, and if we look at this up here, what we're saying is we want to solve for the total pressure. So P total is going to equal the pressure of oxygen, pressure of O2, plus the pressure of the nitrogen, plus the pressure of the helium. Okay, and so we simply take these numbers, in other words 20 kilopascals, plus the pressure of nitrogen, which is 46.5 kilopascals, plus the pressure of helium, which is 26.5 kilopascals. We take each individual partial pressure and we simply add them together. So 46.5 plus 26.5 is going to have to be 73, plus 20 is going to give us 93 kilopascals, and that is our answer. Okay, so there is one more type of problem that we can solve, and that would be type 2. Call that determining the partial pressure. So in other words, in our type 1 we solve for this guy. In type 2 we're going to solve for one of these guys. Okay, in order to do that, they have to give you the total pressure, and then they will give you the other partial pressures that are present in the mixture, but one of the partial pressures will be unknown. So in this example it says the total pressure of the gas mixture is 220 kilopascals. In other words, they give us the total. Okay, and then they say the mixture is composed of hydrogen, nitrogen, and oxygen. What is the partial pressure of oxygen? So in other words, oxygen, that's the one we're solving for, and these guys are known. We know what they are. Okay, so we know that 220 kilopascals has to be equal to the pressure of oxygen plus the pressure of hydrogen plus the pressure of nitrogen. Okay, oxygen is the one we don't know. So in other words, 220 kilopascals is going to be equal to the pressure of oxygen plus the pressure of hydrogen, which is 47 kilopascals, and the pressure of nitrogen, which is 95 kilopascals. Okay, so if we take these two, so this guy here and this guy here, and we add them together, 47 plus 95 is going to give us 142 kilopascals. Okay, we know that the total has to add up to be 220, so we can take our 220 kilopascals, subtract the 142 kilopascals that are created by the nitrogen and the hydrogen, right? And that will give us a remaining 78 kilopascals, which has to belong to our oxygen. Okay, so what that means is the pressure, partial pressure of the oxygen is equal to 78 kilopascals. Okay, so that's Dalton's law. So what I'd like you to do now is solve the practice problem on your own. I will kind of help you out a little bit. Let's read through it real quick. A gas mixture contains oxygen, nitrogen, and carbon dioxide. It has a total pressure of 32.5 kilopascals. If the pressure of O2 is equal to this, pressure of nitrogen is equal to this, what is the pressure of CO2? So in other words, it's a type 2 problem. You're determining the partial pressure. Okay, so do it just like this guy, but use these numbers. Once you get your answer, make sure you enter it in the whisk, and we'll see you tomorrow. Have a good one.